The keynote speaker this morning is going to be Dr. Luca Fasoli. Dr. Fasoli is the Senior Vice President of Silicon Technology and Manufacturing at Western Digital. He is responsible for the strategy and development of Western Digital solid-state memory technologies. Previously, he held engineering management positions at Wafer Scale Integration, ST Micro, Matrix Semiconductor, and at SanDisk after its acquisition of Matrix. He's a 25-year industry veteran, an IEEE senior member. Dr. Fasoli has worked on a variety of non-volatile technologies and solid-state storage products. Leading product development teams from concept to definition to mass production. Dr. Fasoli has published many technical papers and holds more than 90 US patents. Are you going to be in the Patent Hall of Fame soon? So he earned a doctorate and master's degree in electronic engineering from the Polytechnic University of Milan and completed an engineering leadership professional program at UC Berkeley. He is based at the company's Milpitas, California location. Our guest speaker is going to be Max Lowe, who's participating via virtual. So that'll be embedded in it. For those of you who don't know who Max Lowe is, he's a documentary filmmaker for National Geographic. He has a streaming documentary on Disney Plus called Torn, which is a really riveting story about some connections through technology and SanDisk. So let's welcome Dr. Fasoli.
Thank you, Derek. I'm an engineer, and many of you are engineers as well. And so we're not very emotional about the things we do. We all speak about data analysis, schedule, planning, how to get things done. But I want to share a moment in my life in which I became extremely emotional about my work. So I was flying over the Pacific in one of these long intercontinental flights, and I was flipping through channel as you normally do, trying to find something good to watch. And I came across this documentary called Thor by Max Lowe, and I started watching it. And Thor is the story of Max father, Alex, who is a world-renowned mountaineer that died in an avalanche in the Himalayas in 1999. The story is really well said, well told, and it's the story of Max's families as they grapple with the tragedy of Alex's tragedy. But what happened at the end of the documentary is that Alex's body gets found 17 years later in the Himalayas. And in the documentary, they describe the family traveling to the Himalayas to pay the last respect to Alex's body. And with the body, they found a backpack. And within the backpack, there was a digital camera. And in that digital camera, there was a 30 megabyte compact flash card. And when plugged into a laptop, into a PC, it shows the last picture that Alex took. And one of the pictures shows Alex holding up a birthday card for Max, who stand at that time wishing him a happy birthday. Now, having worked on Flash all my life, I felt extremely proud of what we do. When a compact flash camera sitting in the Himalayas, ice cold, through the weather for 17 years, still works. And it can bring back memory to the family. It really meant something to me, and I felt really emotional about it. And so I hope you can appreciate that what we do truly matters to people. It's not only about data, numbers, schedule, risk mitigation, but it's about what we do for whoever uses our product. And so it's our fundamental duty to make sure that those product works. Good morning. My name is Luca Fasoli. As Jerry said, I've been working on non-volatile memory technology for a good part of the last 25 to 30 years. I'm at Western Digital, and in Western Digital, my team build, test, and bring to manufacturing most of the flash product. Over the next 30 minutes or so, I'll tell you a little bit what we do in Western Digital with respect to meeting the demand of the world, of the data storage demand of the world. How do we test for it? And what do we see as the future coming forward? Before I do that, I need to make my lawyers in Western Digital very happy. I need to tell you that anything I told you, I can change my mind tomorrow, and I don't need to come back and tell you because I'm protected with this statement. So now that I'm out of trouble and my lawyers are happy, let me continue. What do I want to tell you in the next 30 minutes or so? I want to convince you of 3 facts. Fact number 1, data storage demand is growing. We will tell you why and what is the motivation behind it. Second, cost reduction is one of the most important things that enables the data demand storage to grow. And third, it is extremely important that we guarantee the quality of the product that we build, and we make sure that data integrity is always there, and it is our foremost concern. Before I do that, let me introduce a little bit about Western Digital. Western Digital is one of the largest data storage companies in the world. We store about 1/3 of the all bits in the world, so I'm pretty sure that each one of us has used at least one Western Digital product in your life, if not more. And either a Western Digital product or one of this brand like SanDisk, GTech, or many others. We, in the last 3 quarters, we shipped 200+ million products, which is equivalent every day of testing 5 million single die NAND equivalent. And in our joint development fab in Yokkaichi and Kitakami with our partner KIC, we produce around 20,000 wafers every single day. And if you stack them up, and all of the wafers that we produce in the factories, we actually would reach almost the height of the Mount Fuji. So that's a lot of wafers right there to test. In Western Digital, we are unique in the industry. We have 2 major business units. One is HDD, the other one is flash. There's a lot of good stuff that's happening in HDD. I will not speak about HDD. I'll mainly focus on flash. And that's what we're going to focus the rest of the presentation. Flash has been disrupting industry since the inception in 1995. We started by disrupting the film photography. Right now, you go around, you can't find any single digital camera. And we've been disrupting very recently all of the laptop market and the desktop market even. Right now, you can't buy a PC that doesn't have an SSD on it. We have the way this disruption happened, the way this market disruption happened, follow a very predictable pattern. First, you create a technology that has a specific cost point. That cost point enables a new application, like digital camera or any other one of those ones. That new application disrupts an existing market and creates new demand. That new demand fosters innovation, foster innovation, foster economy of scale, and further reduce the cost of the bits that we sell. With that cost reduction, what happens? You can disrupt new market. And that's how the cycle restarts. And you continuously disrupt market after market after market. And this is what we call the virtuous NAND cycle development. And through that cycle, in 30 years thereabout, we actually reached the scale of the zettabyte. And I'll tell you a little bit more about how big of a zettabyte here. And there are further industries that will disrupt, because this cycle will never end. We will drive economy of scale, we will cost reduce the bits, and through bit cost reduction, we will enable new applications. We don't know what they are, but they'll be there. And by 2030, we'll triple the number of zettabytes on the chip, getting to above 3 zettabytes. So I spoke about the zettabyte. How big is the zettabyte? Well, it same time to 2021 bits. That's the number of bits in 1 zettabyte. That's difficult to grasp. So let's do this. First of all, if you count all of the grains of sand in the world, it's actually 1,000 times that. So you need 1,000 Earth and count all of the grains of sand to get to 1 zettabyte. It is about the number of visible stars in the universe, and is about 1.3% of the Avogadro's numbers, which is 6 times to the 2023. We engineers love that number, you remember it. So, very, very big number. How do we, in the NAND industry, are able to meet this demand? In the recent past, we've been actually going from traditional 2D NAND to 3D NAND scaling. What does that mean? In the 2D NAND area, bits were put side by side, and scaling happened in the X and Y dimension, basically following the traditional Morse law. In the 3D NAND, we pack bits on top of each other. So basically, memory cells are built on top of each other, and you can increase the amount of bits that you can build in a millimeter square of silicon area. And as you can see, we've been able to achieve all the way to 200 plus layer at 18 plus gigabit per millimeter square, which is way denser than any HDD magnetic storage that you can have. And we see no end to this scaling. We actually can get all the way to 300 plus layer, and we see a way to get to 500 and maybe even 1,000 in the future. Why we do this is because we want to, of course, meet the demand, so increase the bit, but at the same time, you also want to reduce the cost to enable that virtual cycles of NAND development. That's very, very important. Now, before I go a little bit deeper into telling you how we reduce cost in NAND while meeting the NAND demand, I want to spend a little bit of time describing our latest baby, the 218 layer technology. This is a very unique technology. We just announced it. It's actually just went to production a few days ago. And this slide is the first time that gets shared in the industry. And it is a technology in which, rather than building NAND chip in a monolithic wafer, we actually build 2 wafers, which must be very good for this industry. And the 2 wafers that we build, one is the circuit that needed to read the memory cell, and the other one is the memory array by itself. We process them separately, in parallel, and then we bond them together. This allows us to independently optimize the 2 processes, allow us to achieve incredible performance, and meeting the needs of the data center, which is one of the main places where we're looking for disruption in the next wave. You can see a picture right there where you see the 2 wafers and you see the bonding interfaces. And through that, we're actually able to achieve several things. Number one, we are increasing the memory density. This is the way to increase the number of bits that you produce. More bit per wafer allows you to increase the bit production by 50%. We achieved that by in two different ways. Way number one, we stack more layers. We stack 35 more layers compared to our previous technology. On top of it, because we can independently optimize the 2 processes, the array can be squeezed in X and Y dimension, same way as we did in the 2D NAND days, and we actually are able to increase the layer density by 12%. So 12% compounded with the 35% NAND increase gives you 50% higher memory density. Because we are able to independently optimize the array and the CMOS, we are actually able to increase the performance to meet the data center demand. Specifically, our program bandwidth is around 30% more. Our read latency, which is extremely important for fast answering application in the data center, 21%. And amazingly, we've been able to increase the transfer speed, which is the data I/O, by 92%. And this allows us to really build this memory for the data center. So please be on the lookout for product based on this technology out there somewhere to go and check out. So I now want to go back and tell you a little bit how do we achieve NAND scaling. Okay, NAND scaling is two major things. One is bit growth, two is cost reduction. So every time we build a new technology, we always look at those together, because bit growth without cost reduction doesn't enable anything. It just produces more bit growth and causes the industry to crash. You have to couple it with cost reduction. So the way we do it in 3D NAND, first one is pretty straightforward. I already told you a lot about it. You just go higher. Going higher is equivalent to us building skyscraper in downtown San Diego. You don't build one-story house. You build very tall skyscraper because the real estate area is very expensive. So very important for us to go high. It's not the most efficient way. As you can imagine, add one more layer, it has increasingly diminishing return. Every time you add a layer, it becomes more complex to build, and it costs more to build the wafer. So there's an optimal number of layers that you need to add. What you need to do to really achieve a good cost reduction, you also need to do lateral scaling. What lateral scaling means is if you go downtown San Diego and look at the skyscraper, you make the room as small as possible, the wall as thin as possible, the staircase as little as possible, the elevator as little as possible. This is what we do in 3D NAND, very carefully, because you want to compound the effect of going up with also scaling the X and Y. And so you want to increase the bit. And this is a good way for us to increase the bits and reduce the cost of every single bit. The third way is a very classical way to do it. You do more with one single memory cell. Again, going back to my similarity, you go downtown San Diego, it is exactly as putting as many people as possible in the same room and having them paid exactly the same amount. And this is exactly what we do with logical scaling. In logical scaling, we store more bit per cell. And you do that by using the characteristic of an NAND cell, that is an analog cell. You can store multiple different layers independently from each other. And as long as you can store them, program them, and read them back reliably, you actually can have more bits. So for a 2-bit per cell, you need to store 4 layers. For a 5-bit per cell, you need to store 32 independent levels, and you need to be able to read them back. You can understand that comes at a certain trade-off with performance. The more level you add, the more difficult it is to program, and it takes longer, and the harder it is to read them back. So you need to fine-tune the application for each one of these technology to really match workload with the performance of the cell itself. Right now, the bulk of the production is in a 3-bit per cell, and we are in the process of transitioning to 4-bit per cell for 16 different levels. And we see ways to get all the way to 32, but not in the near future. And those ways will have to match application need with the performance. The fourth way and this is, sorry, let me go back. On logical scaling, it's a very efficient way for us to get more bit and cost reduce. Because it doesn't cost you anything to build a 3-bit per cell versus 4-bit per cell. It's basically the same, but you get extra bit and you get the cost reduction, of course. So that's a very efficient way to do it. The fourth vector of NAND scaling is the architectural scaling, which is where do you put the support circuitry of the array to read the NAND cell. Traditionally, you do it in monolithic silicon and you put the circuit on the side. That's a very easy way to do it. It's not the most efficient way to do it. You can put it underneath in a monolithic wafer. Or you can do like we did in Big Safe, building the 2 wafers separately and putting them on top. Each one of us has a different, each one of the way have a different cost, a different bit growth, and a different cost reduction. And so we optimize that, and we believe that the transition of the industry is going towards the multi-level bonding, and we are leading the way in that. The last vector of NAND scaling is something that doesn't help you at all to bit growth, but it can hurt you a lot on bit cost, and that's why we're here. It's test. test has no value add other than making sure that our customer never have to send us back a product. So you can definitely test too much at the cost and never be able to, and then never be able, and completely not meet the need of cost reduction because all of your cost goes to test. And so it's very, very important to really quantify that and continue to reduce cost reduction at the same pace of all of the other 4 vectors. So for the rest of the presentation, that's what I'm going to focus on. How do we, in Western Digital and in the industry, keep up with the NAND cost reduction scaling, this unstoppable rate, and we don't prevent from creating new market because we don't do a good job in testing. Let me tell you a little bit about testing in NAND. Testing in NAND is a little bit different than your classic semiconductor testing. I'll make a very controversial statement, which is NAND is a fundamentally defective technology. Basically, when I was there when NAND was invented, and I had devices engineer coming to me and say, this will never work. And I tended to agree with them. The reason is because fundamentally, you can't rely on programming you can program distribution, but you cannot program one bit at a time. It's not like a NOR technology where you can very precisely put a bit. Bits kind of are always in the midst of value distribution, of the two distribution. And so inherently, the brilliancy of the NAND industry has been to embrace that concept and build product-level mechanisms to cope with this fundamental defectivity of the NAND. And so there is no product in the industry that uses NAND that doesn't have some sort of error correction mechanism already built in there. And so when it comes to test, you really don't have to test every single bit to guarantee every single bit. You need to guarantee that bits get programmed to a level that your product can actually meet the product requirement. It's all about which final product requirement is, not of the NAND component by itself. The other advantage of NAND is that NAND cells get programmed in what we call a block. And a block is the minimum entity that you can program and erase in a monolithic fashion. Because in the field you program block in a monolithic way, you actually can afford a block not to work. So if you program a block, you read it black, the thing doesn't look right, you can relocate that data because you already have all of the data of that block that you were planning to program. And so what you want to do in test, you do want to test for block, you do want to weed out all of the bad blocks, but you don't have to guarantee that every single block will work. You can have a few that don't work as long as on the product side, you're able to recover them. You actually can make the product still meet the very high performance quality requirement that the product has. And so you don't want to weed out all of the bad blocks. You don't want to weed out all of the die with bad blocks at the beginning. You want to leave it at the end. Mark as many as possible and have a minimum amount to go through that is going to be taking care of the product. The die testing level is similar to a classic ASIC testing. Just want to make sure that every single circuit works. If the circuit in the NAND die does not work, you can't program erase any block. So that's something that you have to guarantee, and this is very similar to NAND. So you want to weed out any bad die as early as possible from the process to reduce the cost of that of the yield loss due to die. There are products that actually can recover from a full die or a full package product failure. There are, but you want to minimize those because every time you have to kind of compensate for a die that goes bad, it takes a lot of time to remap all of the data within the product itself. So it has to be in the very low DPPM type of thing. And lastly, as you put your NAND die and put it into a product in a system, you have to make sure that system works. If the system doesn't work, there's nothing you can do. So that has to be tested at the product level, can only be tested at the product level, and you really cannot afford it. So this is kind of an introduction, high-level introduction to NAND testing, which has a lot of sophistication that you would normally not have in standard SoC or ASIC testing. So I want to go back to the necessity for us to innovate in testing. So this is a theoretical chart. You can see in the bar chart is our NAND demand year by year. And what I have done here, I have locked my team back to what we were doing in 2015. No innovation, standard testing, just keep doing it. And this is the percentage of test cost versus the percentage of product. And if you don't do anything, what will happen is that your test cost, and you're stuck in 2015 in the past, your percentage of test cost that goes to test goes up by 3.6x, completely wiping out all of the things that we do in technology. And product costs will not come down as much, and then new market destruction might not happen. So this is a very key point. We must innovate in test. It doesn't get spoken a lot, but test can definitely block the race and block the NAND demand growth because it blocks the way cost gets reduced. So in the next few slides or so, I'll tell you a little bit what we have done in Western Digital, what the industry has done to cost reduce as much as possible. And I'll speak about flows and I'll speak about testing. First one is with respect to flows. Again, we're going back to the concept that NAND by itself doesn't, I don't want to say it doesn't exist, but is not used. It's always used in a system. And so within a system, there's always a certain number of NAND dies and then a controller that manages it. And so we not only use it in the field, but also in testing, we use self-test. Again, it's not a new concept, but we go to the extreme. We use these large, highly parallel, massive machines. We plug in a product. We load the test program on the controller, and then we run it to test, to self-test the NAND, as many NAND dies there are in there. We test for speed, we test for reliability, we test for bad block, we weed out all of the bad block that might be there and mark them as bad before they get shipped out, etc. Very important, great way to reduce test. The second one, I want to go back to that concept, and that you need to guarantee the spec and the quality at the product level. So you have system level capability to correct in the field. So it's not about testing every single bit, it's about testing every single bit so that in the field there is no failure. And so we have been exploring ways to check, do we need to test every single bit? Do we need to do a sampling? Do we need to test every single black? Can we do a sampling? So that at the end, the product quality never gets compromised. And we do that to an extreme amount, thus saving a lot of test time. The third aspect is binning. We call it grading, but it's the same thing. And normally you bin for speed. We don't bin for speed only. We bin for everything that you can think about. Within Western Digital, we build I don't know, 32 gigabyte USB drive that each one of you has in your pocket, to a 128 terabyte drive that goes in a data center somewhere in the desert. This product has completely different requirement in terms of the NAND. So what we do is we try our hardest to find out the characteristic of every single NAND that's in the product, and then match it to every single NAND die that we produce, and then match it to the product that is going to go. And so we bin for speed, of course, we bin for reliability, we bin for number of backlog, we bin for absolutely everything you can think of. And by doing that, you maximize your yield, you never compromise on quality, and you're able to reduce the test. And the third aspect, again, going back to the system management, we leverage the fact that at the end what matters is the product, is the quality at the product level as seen by the customer. And it's a combination of test and field capabilities. And so we manage that very carefully. We figure out what are the defective modes that exist, And some of them we spin up in the test floor. Some of them we make sure that in our product we have a way to cover them up and never have to show up at the customer level. And that requires careful testing of the final result of the combination of the test and the system level management. Speaking of testers, let me speak a little bit some of the drivers for testers. So number one, we have a large number of die per wafer that we test. The reason for that is that the product density doesn't grow as much as the NAND density can grow, and so our NAND die are becoming smaller in terms of physical dimension. So we have more number of dies per wafer. Similarly, we also have a large number of units to test, continuously growing. As I said before, 5 million dies every single day we test, only in Western Digital. You can think about what's the scope in the industry. Third, we have a broad temperature range, increasingly getting bigger. And that's because there are applications like automotive that requires bigger, larger temperature grading. But also because some of the product now goes into a higher power. And so because of that, the temperature requirement at the product level gets higher. And lastly, the host protocol, the way our product gets used, continuously evolve and continuously get higher and higher speed. So how do we manage with this driver with our testing infrastructure? So in terms of the large number of dies, we want one-touch die, no matter how many dies you have on a wafer. I know it's a tall order, but this is something that we really need the industry to deploy for us. We can spend more than one touch time for every wafer. Now, that doesn't always happen, of course, we know that, but that's really our tall order. Because we have too many wafers and too many wafers to test to really have it to do. I can give you an example. We had a wafer that had, so our capability for STAM was limited, and some of our wafer technology had more than the capability we could test. We actually even let the dies that we couldn't test go and build them as bad rather than spending the extra touch down to test it. So that's how bad we need single touchdown to this extent possible. Second, the large numbers, we do need to have a very high parallelism and low cost per DUT, and I'll go a little bit more in detail in the next slide. Second, the third thing, we need to make sure that we test high to low temperature, but we don't want to spend more, so we need to work with industry to come up with very cost-efficient solution that covers all of our temperature range for testing. And lastly, the host protocol evolution is something that really bugs us. Every time you go from PCIe Gen 4 to Gen 5, it becomes like a big deal to have to change all of our manufacturing infrastructure. We do not want to do that. Our manufacturing team does not want us to do it. So we need to have the industry to develop solutions in which as the protocol change, there are minimal amount to the hardware. I'll go a little bit into that. But what we are doing in Western Digital is we're trying to minimize the amount of time that we spend at the host protocol level and try to maximize the way we do internal testing with DFT on less expensive machines that don't operate at the host protocol speed. So let me go into the details, large unit of testing. How do we manage that? Well, we have developed a unique solution in Western Digital in which, taking a page from the book of product testing, we're actually building large, highly parallel machine, very dumb, but we put the intelligence locally where the NAND die is. So we decentralize our testing. And every NAND die has a decentralized tester in there that does all of the testing of the NAND. And we try to test everything on this type of infrastructure. So we go away from having very complex tester, and what we test is everything that we can test in that infrastructure, and then we do a fast read out at the end. And this allows us to drastically reduce our test costs. And then in terms of host protocol evolution, I'll repeat what I said before. As the host protocol changes, we do not want to change the hardware infrastructure. We want to minimize the changes from one to the other. And this has been pretty painful for us as we went from PCIe Gen 3 to Gen 4 to Gen 5. But we really want to have a long-term, scalable, upgradable solution that goes that allow us to sustain it as the host protocol changes. The last piece, of course, I can't do a keynote without speaking about artificial intelligence. It seems to be like the hot topic of the market. We do use artificial intelligence. We have been using it for a very long time. And we have an extremely data-rich test environment. And I will describe two different ways that we're using it, but we're using it in multiple ways. The first one is the best testing there is. It's music to my ear, virtual testing. No insertion, no tester, no yield loss, perfect testing. The tester never works. This is what we do and what we have developed. Of course, we run wafer sort. We collect as much data as possible. We fail nothing. We collect analog information. And then we build models that replicate the need of every single product that we have. So if you're trying to test, if you know exactly what a USB needs, you know exactly what an SSD needs, and you build model to match the die to the product. No testing, just using the data collected in wafer test. And our models are very, very complicated. We have up to hundreds, if not thousands, of different parameters that we look at to match the NAND die to the product itself. And we do that as a simple updating wafer map. We can simulate yields. We can do tons of different things that are really just changing a software somewhere, a software setting somewhere. So very, very powerful. Another way we do it is very similar concept, but slightly different. We go after test time. So again, use the parameter. We look for die that might have more defect on it versus die that are good. We look for signal. Again, we don't detect the defectivity. We just look for signal in the wafer set. And then we package them together, the dies that are deemed good and the guys that might be problematic. And the dies that might be problematic, we test them more so that we can weed out all of the bad blocks from these dies in the package. And so some of them go to a very short test, some of them go to the full memory test. And we never compromise on quality, but we achieve test time reduction. So now that I've told you a little bit what we do in Western Digital, I want to tell you the result for us. How does that compound? How does this test innovation that I described to you, plus a few more that I haven't, how does that come to us? So I told you before, if our team was stuck at 2015, we would increase the test cost, the test cost percentage as of the product by 3.6x. And we actually were able to reduce it to 20%, to 0.2x. And you can see this is the actual data that we have, and this is what we predict to be. And so this is what we have been able to achieve using all of the techniques that I described to you. And this is mandatory. This is absolutely necessary. Otherwise, we're going to get in the way of the big cost reduction and prevent us the next level of innovation to come and increase the demand and meet new applications. Now, looking at the future, what are we focused on? What is it that we're looking at? Number one is single insertion, no matter what. I told you about single touchdown, single insertion. One insertion per form factor. I want to have one insertion at wafer, one insertion at component, one insertion at the system level. That's it. And this is very complicated because now we are not there. But this is what our manufacturing team is, and this is going to drive the next level of innovation. And this is going to be enabled by going extreme on the artificial intelligence models. You have to be able, you want to test everything, collect data in an analog fashion, never fail anything till you absolutely need to. Absolutely need to. So very important to have a test infrastructure in which analog data gets collected and artificial intelligence model can be built. And lastly, the next level is real time. As I said before, we can't afford to make decisions on our test too late, because otherwise there are too many dies that go through, too many wafers that go through. We want to have real-time data, being able on the fly to adjust our test as we see things happening either in the fab, upstream, or downstream at the customer level, so that we can react in real time and be sure that we don't have any incident in which quality gets affected. Again, not an easy thing to do, but extremely important for us. So going back, are we ready for the zettabyte era? So I hope that within these 30 minutes or so, I give you a sense of how we're thinking about what are our kind of long-term things that we care about. Having extremely efficient test flow with higher parallelism, with lowest cost solution. Power consumption is starting to become a big issue even in our test infrastructure, so something to look at. Complete reuse of the platform in the manufacturing team, in the manufacturing environment. Artificial intelligence is going to be a cornerstone of our future development. And then lastly, we do want to have standardized test infrastructure, because otherwise it becomes very difficult for us, as memory storage manufacturer, to really be able to mix and match and have an effective way of testing. And this requires really a collaboration between us, all of the 88 vendors, this audience here, and then of course have a deep understanding on all of the product requirements. And so I hope that I've been able to convince you that data state management is growing, cost reduction is extremely important, including test, but you definitely don't want to affect quality. And speaking of quality, I want to go back to the say before. I want to go back to Max's story and how he told the story of Alex. This is him as he was 10 years old with Alex, and this is him today. We wanted originally to have an embedded presentation from him calling in, but I think we have some technical difficulties. So, but I think it's okay because Max is actually here with us. So Max, come on up. I'm gonna ask him to tell a little bit about his story, about how he uses some of the product that we build, and please, Max.
Thank you. It's my well, thank you so much, Lucas, Felix, and the whole team here at SWTest for having me down to beautiful, gloomy California. June gloom, I know. Stories are everything to each and every one of us. Each of us lives our own story and perspective of our own experience within our families, within our communities, within our cultures. Those stories are what root us within our life experience. My dad, Alex, pictured here, doing something crazy, standing on top of a much too small rock on the top of a massive mountain in the middle of Antarctica, Queensland, lived quite a story. He was actually an engineer. He went to school in Montana, got his bachelor's degree in engineering, and went on to get a master's and worked for Schlumberger briefly before he was able to push through into what really drew his passion, which was climbing and mountaineering. And he was able to take that passion and grow it from a seed into something that would encompass his life. And he was able to make that his life. It was this thing that he dreamed of as a kid, being able to do much more for himself, and eventually he was able to make it his career. And it took him all around the world. It took him to some of the highest mountains on earth. He climbed Everest 3 times during my lifetime, and was able to explore some mountains and parts of the world that no one had ever been to before. And he always took us with him. This is a picture of me and my two younger brothers, Sam and Isaac. He struck this balance in his story between what he was passionate about, this thing that made him whole, and the family that he left behind that supported him and held him up. And I think that, in thinking about his story as his eldest son, this is something that really drew me in when I first started thinking about my life as part of this larger story that Alex and our family had lived. How we strike that balance between what we love and what we need to do for ourselves and the people around us that hold us up and support us. I think that that's something that any one of us in this room can relate to. In his mountaineering and expeditions around the world, Alex found a best friendship in his partner, Conrad, here. You can see there on my left, it's here his left, I guess, holding hands. And they were bonded by this shared passion for mountaineering. Pushing the edge of what we know, in the physical world, pushing that edge is something that bonds us as human beings. We're stepping into the unknown, and it's something that everyone in this room, I'm sure, knows to some extent. Pushing the edge of what we know as human beings is possible, and going just a little bit further, unsure of whether or not it's going to pan out in the end, but the risk is worth the reward. Right? In 1999, as Lucas mentioned earlier, Alex and Conrad were on an expedition to climb and ski an 18,000 meter peak in the Tibetan Himalaya called Shishapangma. And on one of the days leading up to the push to the summit, they were doing a scout mission to go and look at part of the route. And from up on the top of the mountain, a serac broke off, which is basically a big chunk of snow that hangs over the edge of the mountain. And a massive avalanche came thundering down onto Alex, Conrad, and one of their other partners, Dave. Conrad ran in one direction, and Alex and Dave ran the other. And when everything settled, when the snow and dust from the avalanche had all kind of stilled out, Conrad stepped out of the snow and looked around, and Alex and Dave were gone. And in that moment, Conrad's life changed. He recognized that fact. It was something that was very clear to him in that moment, and it would become clear to myself, my mom, and my two younger brothers, as well as the rest of the world. This was a global event. Alex was a character in the world, in this much larger story that he was a part of. And his death was a global news event. And for me, as his son, this was a confusing, complex thing. Obviously it was crushing. My dad was a huge part of our world, and my understanding, and my own reality, and my story. And losing him in this way where he just disappeared. He was like an astronaut lost in space, never to come home. As a young 10-year-old kid, I was on the cusp of turning 11. I turned 11 5 days after Alex's death. It just broke my world understanding down. It kind of remained that way for a good chunk of the rest of my life. Conrad ended up coming back from that expedition, and through the shared grief that he and my mom both had in the wake of Alex's death, that ended up coming together, and eventually I got married. And Conrad kind of stepped into my brother's and my mom's life and took up the place that Alex had left. And we lived in this story, it was the story of Alex's life and death, and the story of Conrad's survival and stepping into our family. And many people told this story. It's a dramatic story. It's a story beyond fiction. And I was just a part of that. I was this kid who had lost his dad and had struggled to understand why all this had happened and the choices that were made outside the scope of my power. And 17 years after Alex's death, something unexpected happened. Two climbers were going to climb and ski the same route that Alex and Conrad and his team had set out to attempt to climb themselves in 1999. And they stumbled upon some shreds of fabric coming out of the snow, which ended up being the remains of my father and his partner Dave, melted out of the glacier 17 years later. And for me, this just blew my mind. I think as a little kid, I had just stowed this all away in my past and never really went down the rabbit hole of exploring, this story, this massive story that informed my entire reality too much because it was just too painful. We had this trove of archive. Alex's life had been captured in fine form by cinematographers and photographers over the years. He was on the cover of Outside Magazine. He was in stories with National Geographic. We had this massive filing cabinet of slide film, which some of you might remember, in our basement. But I had just never really wanted to go down that hole. But when his body was discovered and this story was unearthed for our family, it changed everything. And as a family, we decided to go back to Tibet together. To put his body to rest and to address this story left hanging for all of us.
The bodies of American mountain climber Alex Lowe and cameraman David Bridges have been found on a mountain in Tibet.
It was like he came back to life. He showed up,
Yeah.
Feelings of trepidation. What will it be like to see him after 17 years?
Surrounded by the most breathtaking vistas, but it's also tainted by the reason you're there.
The bodies of American.
That was a little excerpt from Torn, the film that Luca was able to catch on his Trans-Pacific flight. And a film that I started to document on that trip to Tibet. With the permission of my family, I wanted to capture this experience. At very least, just as a way to look back on this journey that would again turn my life and the life of my family upside down. Having these memories so that we can reflect upon them at some point down the road. And it was in the subsequent months when we returned from Tibet that I really started thinking about my place within the story and how this story had been something far and above beyond what any one of my individual family members can reconcile with or grasp for themselves. And it was also in those subsequent months that we decided as a family that we would open up this camera that Alex had on his person. And that was this little gem that came out of that experience, that we could all open this camera together and see if it was still operational, see if there was a memory card in it, and see some of the last things that Alex had thought of. And the story would become something much bigger than any one of us in our experience. But for me as an individual, that moment of opening up the camera was a remarkably special and vulnerable moment within the process of telling the story.
You're probably listening, or my guess is.
It's nice, yeah. We try to clean it off a little bit. Yeah.
What is the name of the actor's one? And Conrad was that too.
Before you travel, and make sure it's accurate.
Yeah.
Well, moment of truth.
There it is. Loaded.
Oh, Max.
Yeah, the birthday card, I remember he did that.
Wow, that was last night.
So I received this card in the mail a few weeks after Alex's death. He had sent it from base camp in Tibet, and for my 11th birthday. And it was this thing that, kind of immortalized him to me. Initially, I thought that, in my child's mind, it meant that maybe he was still alive. Maybe he was still out there in the world sending this memento of love back to me, his son. And subsequently, it just became this thing that meant he thought of us as his family in this moment where he was juggling his decisions in life, how to pursue his passion while also balancing the love for the people that held him up. And so to have this be the last photo that he had taken that morning before he was killed in the avalanche, and to have it preserved over all those years meant everything. I have that memory card with me actually right here. 30 megabyte compact flash SanDisk memory card. I pulled it out of that camera and plugged it into my computer and it booted up, and I was able to step back in time and access this part of myself that I had left behind. And, I'm sure that in your guys' day-to-day jobs, you're not thinking all the time about how this impacts people's lives, the work that you're doing. But as I said before, stories are everything to each and every one of us. We're lucky nowadays to have phones in our pockets where we can capture every moment of our lives if we choose to do so. But the memory in those phones and the memory in the cloud that our photos are uploaded to, and the memory that we capture and store every story created on Earth now is all in your guys' hands. The history of humanity going forward is in your hands. It's passed on human to human as well, but these little pieces allow us to understand ourselves in a deeper sense. A story mouth to mouth is a powerful thing, but a story when you're allowed to tell it yourself, store it yourself, and within your own perspective, and share it with the world is a remarkably powerful thing. And I can speak to that firsthand as a storyteller. Sitting down with my family, this was an exercise of trust. They were trusting that I was taking our shared story into my hands with delicacy and grace. But they were also trusting that I technically knew what I was doing when I was setting up all these cameras with my team and setting up the technical infrastructure to sit down and have these conversations that in some cases, in these interviews, I had never had with my family before. And certainly couldn't have a second time the same impact. And so in my line of work, I'm in the business of trust. I'm sitting down with subjects, in this case, my family, in a remarkable sense. And they're trusting me with their stories. They're trusting me with this experience that is sometimes painful, but almost always powerful, in the sense that they are taking a hand in shaping their own narrative with my assistance and with my support. And that takes my trust in the equipment that I'm working with. And this is my stepdad, Conrad, and my two younger brothers, Sam and Isaac. My brother, Sam, is actually in the film industry as well. He's an AC, and Isaac is now a graphic designer, so we all work in the creative space. And it's just cool to think that each of us has kind of stepped into our own narrative, shaping our own stories now. And in that, we're each engaging with this world that you guys are all in behind. But as the consumers that Luca was pointing to at the bottom of the graphs he was pointing out there. I have had hard drives fail on shoots. And, over the years they've gotten better and better, but that is a crushing blow, because you've lost something that will never be recovered. You can put everything into a production. Money, line items go into the crew, getting you to these remote places. Everything that goes into capturing a story in real time, something that will never happen again. But if those hard drives that you have put every bit of your resources into in the end, you're holding a little piece of history in your hand. You're holding every bit of resources expended to get there and tell that story in your hand. And if those aren't insured to last and to work when you get back home and plug them into your computer to start the post-process of working on these films, telling these stories, then everything else is moot. And I think that comes right back to Luca's work. These guys are developing these things. But when it comes down to it, if they're not tested to the point where you can 100% guarantee them, then everything else doesn't even matter. If I am using a product and it fails on me once, it snaps in my mind, that's not a trustworthy product anymore, and I'm not gonna buy it anymore. There's so much pressure on me as a storyteller going into these situations to make sure that every part of the process works. And memory, storing these memories, storing these stories is one of those pieces that I often don't think about a ton while I'm out there in the field, but it's one of those things that I just rely on. I rely on it to work. And it's really cool to stand in a room here with all of you who make sure that I can trust those products to bring home stories and tell them to the world. Just wrapping up, this is one of the last images that I took when our family went to Tibet. And for me, going back to Tibet and facing the story that had defined my life, facing my father's remains and going through this experience with my family that was beyond difficult. There was a silver lining in that I got to go and live first person these stories that I had always heard secondhand. Alex would come home with these photos and stories and send me postcards from afar that sparked my imagination as a kid. I think it was the stories that I got secondhand that allowed me to believe that a life like the one that I'm now living was possible for me. And, stories are something personal for each and every one of us, but they're also something that we give to the world. It's a gift to be able to go and have a unique experience, whatever that might be, but then also share it with others so that they might be inspired to push that edge a little bit further. I think that is probably, for all of you as well as myself, something that you hope in your work, not only to further the world by your own means, but to maybe inspire someone else to do the same. And going over to Tibet and being able to capture these images myself and share this story with the world was that edge that I was pushing. I wasn't stepping into the unknown in the physical sense that Alex was, but I was stepping into the unknown as a storyteller in hopes that I would inspire some person on an airplane to maybe think about their own life and their own experience in a different way. So I want to thank all of you for the work that you're doing, because it 100% enables me to do the work that I do, and I couldn't be more grateful. So thank you for having me.